All right, so we've seen several projects here that I've created, kind of gone from the place of things totally not working to things actually working pretty decently well. So you can see that the project name that I still have over here is Hello World. So what we're going to do is we're actually going to close the open projects that we have, and we're going to start from scratch. And the reason I want to do this is just so that we can kind of look at all of the things that are involved with starting from scratch and the configuration, just because it is different than, and you can get lost essentially. So it can be a little bit more complicated to actually get a project up and running than if you already have a project that's up and running and executing and all that kind of stuff. So just to make sure I haven't glossed over any of the parts of creating a project, I'm going to go ahead and create one now. So I'm just going to go to File, New Project. So here is a really excellent example of where you could kind of get stuck a little bit and not really knowing where you're going to go. So the default here is a 32-bit MPLAB Harmony project. So Harmony is essentially a framework. And it's sort of built around the idea of simplifying some of the programming by having easier functions that are kind of grouped up and niceified so that you can use them easier. I have not worked with Harmony hardly at all. I'm sure it's a great product, but part of the attraction for me to pick microcontrollers and small processors in general is the fact that you're really close to the metal. And you can do things incredibly fast, and that is, that you can actually be really honestly manipulating silicone and manipulating, small latches and stuff like that that really affect the way, transistors are operating. Harmony to me feels a little bit more like a operating system to a certain degree. It's very task-based, which is great in certain things. Like for example, I haven't done an example yet of like a USB or a wireless networking tutorial. That's one of the cases where you really have to be really spot on your timing to make sure that you're doing things correctly at the correct times and you're setting the bits correctly up, down, and so on in order to send the signals correctly. And that can be complicated to do by hand. So I'm not even sure if it's really possible to do by hand. We'll have to find that out later at some point when I kind of dive more into that and say, hey, let's try and get networking working without using Harmony. And start reading the documents and doing all that. So for now, though, we want to do a standalone project. So I'm just going to call this thing demo project. Oops, wrong place. Standalone project, and then hit next. So the device now. Devices recently used is cheating because that's the device that I want to use. So if you had to do all families, this is a very long list of the give or take 2,000 different microcontrollers that Microchip makes, as well as all of the AT. I think the AT series is in here, the Atmel or whatever. Microchip purchased them. Yeah, AVR, Mega, Mega Tiny. So there's more in here than just the PIC processors, but you see a PIC MC use, PIC32C, PIC33, DCS. So you've got different controllers for sort of different things: 8-bit, 16-bit, 32-bit. And really, all this does is help you select from the smaller list down here. So even if you get yourself to a PIC32, you still have a tremendous list. So really, the biggest thing here is finding out what processor you have. You've got to know that number. And I already have it, like I said, in the recently used. There's two that I really work with. This PIC100 or this PIC10 F200 is a very inexpensive processor. It's about 58 cents. And then this processor right here is the processor that's on the Curiosity board, the PIC32MZ Curiosity board. So that's the processor that we want to use. And you'll notice that Curiosity board is not a selection here. You really have to specify which processor you're looking for, which chip you're looking for, and know what it is. So I have the starter kit plugged in, and because I do, I'm seeing this starter kit show up right here. So assuming that you have all your drivers loaded and everything like that, it should show up at this point. I unplug it, it will no longer be there. So you can kind of look through, but it's not ever going to show that there's a starter kit that you can use. If that's where you're at, just select simulator. That's fine. You can always change it later. If you do have a development board, make sure it's plugged in, and it will. You can hear Windows, but and there it is. So, and it will load in some defaults for debugging on this board. Really, mostly it's just setting this in the configuration and creating a configuration. This is the name. You can always create your own configuration. Okay, tool chains. So, just sort of to explain what this is. I've gone into this in other videos. But if you're importing and trying to use somebody else's code, please try and get their version of the C compiler as well. This is the XC32 compiler. That is different than the XC16 compiler and different than the XC8 compiler. So Microchip actually really makes 3 different compilers, the 8-bit, 16-bit, and 32-bit compilers. They are not cross-compatible precisely. There are some functions. There's some functions available in the 8-bit compiler that are not available in the 16 and 32-bit compilers. So it's not that XC32 just adds to the previous ones. It's not like that is a superset of 16, which is a superset of 8. It's really not true. They are distinctly different. Delay is one of the commands that is available in XC8. Super helpful. Delay for a certain number of milliseconds. It makes it really easy to program, and you don't have to do the crazy loop stuff that we've had to do in some of the previous videos. Not available in 16 or 32. Since we're starting from scratch, I always recommend you use the latest compiler. Also, you'll see this somewhere where it says tool chains. Essentially what a tool chain is it's just a series of programs involved in compiling. That's really kind of the way you should look at it. So there is more than just compiling code that goes on. There's compiling, linking, converting to hex and object files, and there's some library stuff. And if you have Harmony, there's even more library stuff that's kind of imported in doing that kind of stuff. That's really what they call a tool chain. So is really not just your compiler, but your compiler plus all your libraries and your executables and all the debug information, that kind of stuff. That's what's in your tool chain. And it's your chain of tools to make sure that you can execute everything you need. So we're just going to select the version 1.44. Project name. Well, we're going to call this demo project. Demo project. Perfect. Set as the main project. That's great. Encoding is ISO 8859. I wouldn't change that unless you have special needs for language. So I'm just going to say finish. All right. So it creates us what? Nothing. So this project is completely empty, basically. It has no headers, it has no libraries, it has no source files. It has a make file that is generic, and that's it. So first thing we need to do, add a source file. So we are going to add a C source file. And I think we actually want to add the main. So when you see the difference here, so a source file just says a C file, no contents. C main is a C file with a main function that includes the standard IO and standard lib header files. So let's go ahead and create C main. And we're just going to call it new main. Yeah, sure, that's fine. And it should actually put it in the correct place. So I believe if we refresh over here, actually don't see refresh, it should actually be under source files. Maybe I didn't create it under a directory. But let's see if we can build it. Project demo is empty. Okay, yeah, I didn't do it right. So let's add existing item. Oh, look at that. There's a C file right there. New main. Okay, no. So obviously I did that wrong. Definitely when you do that, when you select the main, when it says add to a folder, you should probably browse See, that's interesting. It doesn't give me what I would expect there either. So I don't know. I don't really know how they expect you to do that correctly. Maybe they expect you to do it from here, right click here as opposed to doing it at the project level up here. I don't know. Doesn't really matter. So, all right. So, since we're working with this PIC chip, the easiest thing to do is to just turn on an LED. That's it. We're just going to turn it on in a while loop. So we turn it on and then we run a while loop and it just runs forever. That's really kind of the easiest thing. So the first thing we'll do is just do our while one and then do essentially nothing. So this is going to be run forever. So it's just going to loop, 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 loop forever. So whatever we want to do, we can just put up here. So remembering back, I'm actually going to copy some code over from the previous, just so we can sort of walk through this again. So the TRIS registers, TRIS registers, block E of the TRIS registers. These are special function registers, and what we are doing is we are setting this to be outputs. Outputs are 0, so sort of O for output. I'm not sure why they did that. And the 1 sort of looks like an I guess. I for input. I don't really know, but I guess you can kind of think of it that way. Anyway, zeros are outputs. So the LEDs for this development board are on outputs in block E, pins, or output numbers 3, 4, and 6. So what we need to do is we need to create a binary string that sets everything as inputs except for 3, 4, and 6. So 3, we're counting from 0, so 0, 1, 0, 1, 2, 3. Then this is 4, that's also an output, 5 is not, 6 is, 7 is not, 8 is not, and 9 is not. So we have this binary number right here, and we can use our handy dandy binary calculator that Windows provides us. The way you get to that is it's a standard calculator, standard Windows 10 calculator, and you just go to program. Programmer mode, and it helps you out. Click on binary, and you just enter that number, which is 1101, excuse me, 1110, 100111. And it puts a space just like I did for every 4. So you get 11, 10, 10, 0, 1, 11. So 1, 1, 10, 10, 0, 1, 11. Okay, and then you can see right here that the hex is 3A7. 3A7, which is right here. You always have this be 4 bytes, so it's, again, I don't really know why, but it is always 4 bytes. So you just do 0 at the beginning, 3A7, and you're good. You can just set that into the entire register. So we're actually going to do 1 here now manually. So what we want to do is we want to set a latch, L-A-T, latch, for block E. So it actually comes over as late. And we need to set bits as well. So what we're trying to do is we're going to do virtually the inverse of this. So we want to, so I have the code here that says inverse of, but we want to just have the regular then. So let's clean out what we want. 0, leading zeros don't matter, so we'll just delete this. So what do we want to set to 1? 1 is an output, so we want to set pin number 0, nope. Pin number 1, nope. Pin number 2, nope. Pin number 3, yep, we want to set that to 1. All right, put a space in there. Pin number 4, yep, we want to set that to 1. 5, no. 6, yes, we want to set that one. So what we have here is 101 space 1000. That's what we have in our binary. So 101, 1000. So that is a hex of 58. So again, we want to use this notation here. So this being the notation for all zeros, 4 zeros, we just want to put the 58 here. So put 58. Again, the reason is, not that, this one, is it's the hex version of this binary number. Leading zeros don't matter. You can see that it added a 0 there. You can add as many zeros to the left as you want. Doesn't matter at all. So we're setting latch in the E block to this. Now, you can't actually directly set it. You actually have to add the word set to the end. So you're setting this. So it's latch E setting. The reason is because there's other functions you can do besides just set. If you hold down Control and click link, it can't load it in, and the reason is I'll show you in a minute. Ordinarily, what it would do is it would show you the header file associated with this, but we don't have a header file included. So we're actually going to remove all of this code right up here. Just delete it. Don't need it. You can leave your name and stuff in there if you want. I don't really care about that because this is just a demo. Doesn't really matter. And then what we're going to do is we need to create the configuration bits. So you go to Window, then you go to Pick Memory Views, and you go to Configuration Bits. This took me a very long time to figure out what you needed up here. This is an amazing tool. It loads in every configuration bit based on the chip that you already said when you created the project that you had, and it says, okay, what do you want? You want to turn this on? You want to turn this off? You want to turn this on? You want to turn this off? And it creates all this stuff for you. You could go through and modify this to your heart's content. I am actually going to leave it exactly as is and just hit Generate Source Code. And then it dumps out this huge amount of code. You just copy that and put it right into the top of your C file. You'll notice that this is the PIC microcontroller that I selected during setting up the project. So it creates all this config for you. There's nothing you need to do. It also includes this file. This is a generic header file that it includes. So this is a valid file for 16-bit, for 8-bit, for 32-bit, for all of the different processor types. You used to have to actually put in the family, essentially, here in your header file back in the MPLAB 8 days and prior. Now it just sort of auto-recognizes it based on your project configurations in here. So we are basically to the point where this should run. I do want to show you one more thing, and that is this little drop-down thing up here. So a lot of the configuration that we set through creating the project is actually available in this drop-down right here. So you can see here, we only have one. We just have default. And when I click on Customize, it says Configuration Default right here. You can add configurations, you can hit Manage, and you can duplicate, yada, yada. You can have all sorts of different configurations, including you can actually switch. You can actually add another configuration that runs the simulator, or you can just select the simulator to be the running code module, where this code runs from here, and just hit Apply or hit OK, and you'll have switched it. So the same thing with the toolchain, the compiler, even the device you can change up here. So everything is pretty much compatible to be changed on the fly based on these project properties. So you did set them all through the configuration in the beginning, but you can change them here if you want to. So let's just go ahead and run this. Let's just see if we can build it. Build clean main project. Let's see if it builds. See if we messed up anything. Hopefully we didn't. It's always better when you don't mess up anything. Of course, messing up things is how you learn. Trust me, I messed up plenty in order to get here. Man, these header files especially, or these configuration bits. It took a very long time for me to figure that out. So, all right, so it looks like it ran, or built, and it says loading complete. So let's just go ahead and load this onto a chip. Like I said, I do have the USB plugged in, so it should load successfully. It always rebuilds it for some reason, and then you'll see that it's coming over here to starter kit on board, so it knows that it's a starter kit. The reason is that the starter kit's important is that it actually has the debug chips, the debug header on the board itself, as opposed to if we were just working with the chip itself, we would need some sort of, oh, connection failed. That's interesting. If we had, we'll just, if we had some other chip, or if we just had a chip on like that, we would need to have a like a separate debugger, you know, like a PIC debugger, for example. Connection failed. Oh, Maybe that was from last time. Yeah, that was from last time. Oh, there it goes. Yep, found it. Device, program, configuring memory. Cross your fingers. Yay! Programming complete. Excellent. And I can actually see on my board here, which I will attach a video here of at the end, that it has indeed illuminated the correct LEDs. So, 20 minutes, a little long-winded, but that is starting a project from nothing on the Curiosity board, the PIC32MZ, and that is getting it working in the latest version of MPLAB with the latest compiler as of January of 2018. This is the code you need to get it running. And really more important than the code, it's really the steps that you now know in order to get this running. This program is very simple, but you can expand on this now that you have something that will actually work. So I'm going to attach a video here of the running board. Call it a day. Alrighty, so we have our microchip Curiosity PIC32MZ board right here. It is not currently powered up, so I'm going to plug it in. That will start booting the chip up. I actually did load the program on there. You can see it is actually already executing with those LEDs illuminating, those 3 LEDs. Pressing on the master clear button will cause them to go off, and then it will cause them to come back on as soon as the program reloads. So this is the first successful test that we have here of doing a very simple program on the Curiosity board, the MZEF PIC32 Curiosity board, of getting that functioning up and running with a complete project. So